Welcome everyone, and thanks very much for watching our session today. My name is Suzanne Foss, and I'm the product manager for ArcGIS Velocity. I'm joined today by Greg Christakos, who's one of our product engineers on the real-time GIS team here at Esri. So we'll get started with a high-level overview of ArcGIS Velocity and the use cases that it's designed to support. So as we all know today, the world is increasingly connected. This is going far beyond computing systems and our mobile phones, and it now is down to sensors and devices that can measure almost anything. It's been estimated that by this year there'd be 20 billion connected things in the world. And while a lot of these connected things are consumer focused, there's also a huge growth of devices that support industry and business applications. And there's a variety of reasons for this explosion in connected devices. One major reason is devices are becoming cheaper. So more and more organizations can afford them to purchase them and deploy them at reasonable costs. But the growth in connected things is also because devices are becoming smarter, allowing businesses not just to record observations, but also to perform actions at the edge and then trigger alerts based on those observations. Now, given that roughly 80% of sensor data or more has a location component, there's a really wide variety of geospatial use cases in the Internet of Things. A lot of these are horizontal, so they're applicable across different industries and sensors. For example, real-time data from sensors about employee locations can be combined with information about the immediate environment around them to help keep them safe, but also to gain insight from movement analytics to help optimize their work and their allocation. And resource optimization is of interest when you're tracking any kind of asset, whether it's a fleet of vehicles or even valuable hospital equipment. Organizations are wanting to understand where things are, how long they're spending at work sites or particular locations, and therefore how they might allocate them better. And then a lot of organizations also want to leverage contextual data to protect critical infrastructure. So this might be monitoring weather hazards against facility locations. That's a very common workflow. But increasingly, it's about monitoring any kind of threat against any kind of asset of interest. Is it generalized infrastructure, installed hardware in various places? Is it my employees moving around that I want to monitor against threats and so forth? And then there's geospatial use cases in the Internet of Things that are more specific to different industries. So in the utility space, there's SCADA integration and operations monitoring. In the agricultural and environment markets, there's crop monitoring and air quality monitoring. And in transportation, there's an increasing number of roadway sensor deployments to bring in data from connected vehicles. And especially local governments are looking to be able to mine this data and understand micro traffic patterns. So the list of use cases really goes on and on. And ArcGIS Velocity is a new capability that extends Esri's Geospatial cloud with real-time and big data functionality to address these kinds of use cases. So ArcGIS Velocity provides a wide variety of capabilities to ingest and work with sensor data. You can just configure out-of-the-box connectors to bring in data from IoT platforms and third-party APIs. It's also an end-to-end system for analysis, supporting analyzing sensor data in real time, in near real time with scheduling, micro-batching analytics, and also over time. And you can also take immediate action as a result of your analysis. So not just storing data to visualize the results, but you can also send notifications or trigger a process in another system. ArcGIS Velocity falls into Esri's real-time visualization and analytics capability in general. It's in many ways a parallel product to our real-time and big data capabilities in ArcGIS Enterprise. So in Enterprise, GeoEvent Server enables end-to-end situational awareness, analytics, and alerting for data in motion. And when data grows over time to large volumes, GeoAnalytics Server comes in as the solution to process that data efficiently. ArcGIS Velocity is the parallel to those products but in the cloud. So it has GeoEvents capabilities for real-time incident detection and alerting, and GeoAnalytics capabilities for big data summarization and analysis. So next, let's dig a little deeper into how ArcGIS Velocity works. At a conceptual level, Velocity sits on the edge of Esri's Geospatial cloud, and it complements Internet of Things platforms by enabling you to bring sensor data into ArcGIS for geospatial reasoning. So as sensors are being deployed out in the field, they're increasingly being onboarded and connected up to IoT cloud frameworks like Azure and AWS, or made available through data vendor APIs. ArcGIS Velocity can subscribe to or query those kinds of platforms directly without requiring developer-level integration. Sensors out in the field or real-time data coming from mobile devices could also drive data directly to ArcGIS Velocity, for example, over a REST endpoint. Now, the capabilities of ArcGIS Velocity are surfaced through a few new types of items in ArcGIS Online that users configure. So first, there's feed items where you configure bringing in real-time sensor data. They're user configurable components to make connections to real-time data. With real-time analytics, users can perform real-time processing of real-time data and include triggering alerts and actions as a response to the data that's coming in. And with big data analytics, users can access and analyze repositories of historical observations, whether you've been collecting that data to ArcGIS and storing it in a feature layer, or whether your historical observations are in another cloud data store elsewhere. With both of these two types of analytics, you can generate geospatial content as the output, like stream layers, feature layers, and map image layers. And these can be leveraged throughout the ArcGIS platform in client applications, in APIs, or in desktop applications to drive additional insight and situational awareness. The feeds and analytics are configured with the ArcGIS Velocity web application, which is a new application in ArcGIS Online. Overall, ArcGIS Velocity is very much an engine. It's a cloud system that runs real-time and big data jobs, and the application is an authoring experience for those hosted capabilities. The new item types, these feeds, these real-time and these big data analytics, essentially map back to essential challenges with IoT of ingesting data, alerting when incidents are detected, and doing analysis. So next we'll take a look at some of this in action. For that, I'm going to hand it over to Greg, who's going to show us how you can create feeds to bring in real-time data.
Thanks, Suzanne. Before we dive into the details of real-time data ingestion using feeds, I would first like to show you one example of what a feed can offer. None of us are a stranger to the rapid pace of technology. Around us all, we see a plethora of connected devices and sensors that offer increasing amounts of useful data that we can act upon. And as the Internet of Things continues to grow, different entities such as cities are looking to use much of this new information to improve upon the quality of public services that they offer. Public safety is one such example where the right information can make a difference. So let's look at a map where we can start to see some of this in action and get a better idea of what a feed provides at the same time. So here we have our web map, which happens to be centered around the downtown area of Las Vegas, Nevada. If we look at the intersection in the middle, you'll note that we have insight into anonymous pedestrian crosswalk activity. This is made possible using Cisco's LiDAR sensor technology that they've positioned around the intersection. As pedestrians enter crosswalks and pass through the general location, that information is collected and pushed from Cisco to ArcGIS Velocity using the Cisco feed type. It is with this feed that we can take this raw data, process it, and visualize it in real time. So again, we're quickly able to see the real-time location of pedestrians as they traverse the intersection and its crosswalks. While visualizing this type of information can be useful, it becomes very powerful when we start to analyze this data to better understand what is happening on the ground in real time. For example, we might want to know when pedestrians consistently cut across a crosswalk, as this might mean that there's an obstruction in the road that is diverting foot traffic. Or, as we'll see in the next demo later, we might want to be notified when a pedestrian enters an intersection for an extended period of time. Again, more on this later. But these are just some of the questions we can begin to explore in real time with the data that the feed provides us. So let's take a closer look now at ArcGIS Velocity and the simple process involved to make a feed. Here we have the homepage of ArcGIS Velocity. From this point, we can review our latest activity, create new feed or analytic items, or even review various help topics. Now, configuring a feed in ArcGIS Velocity is a guided experience that quickly and easily allows you to bring in your real-time data. If we click on Create Feed, you'll see we're presented with different feed types to choose from. For example, if we wanted to pull data from a feature layer as feature records, we could click on the ArcGIS category seen here and choose to pull data from a feature layer. There are also options for consuming data from cloud providers such as Microsoft Azure, Amazon, and Cisco. We'll come back to this in just a second. Last but certainly not least, we also can configure a feed to obtain data from various web or messaging services. This might mean pulling a website endpoint for data as one example, or consuming data from a Kafka topic as another. In the case of this demonstration, we originally configured a Cisco feed to consume records from Cisco, so we'll go ahead and click See All under Cloud. Next, we'll want to click on the specific feed type, Cisco Kinetic EFM, to get started. Now, the first step you see here is ArcGIS Velocity asking us to provide some key properties in order to establish the connection to the Cisco broker. Depending on the type of feed that you choose to use, these properties will vary. For now, I'm going to specify the host name of the Cisco broker where the intersection data is being pushed from. Below that, I also need to specify a port number in which the Cisco broker is accessible. I'll also specify a client D of my choosing, as well as the topic name where the specific streaming pedestrian data can be found. Once I provide all of this necessary information, I can proceed to the next step. Now, once the connection is established, ArcGIS Velocity samples the stream of data, parses it, and then tries to derive the schema for you. At this step, you have the opportunity to correct the schema in any way you might want to. You can adjust the name or data type of your fields, or even drop any fields you don't want for further processing. The next step, however, is to identify key fields within the data, including how location is represented, date and time properties, as well as identifying a unique track ID. In the case of the data coming from Cisco, I know that my geometry is coming from X and Y fields, so I'll choose that as my location type here. I can then set my longitude and latitude fields accordingly from the dataset and specify an appropriate spatial reference. For date and time values, the timestamp of each observation comes in as an epoch timestamp, so I can set that here. I also know that the time field I'm interested in is TS for timestamp, so I can set that as well. Lastly, I want to specify the track ID from my data. A track ID is used to uniquely identify each entity or track in the data if you're getting data with multiple observations of the same thing. In this case, I know that there will usually be a few observations for each pedestrian while they're in the range of the LiDAR system, so I will set my track ID field to be my PSM ID field here. And with that, I can go ahead and specify a name and an optional summary description, and my feed is good to go. We're basically finished at this point. Again, a feed is a new type of item in ArcGIS. It includes the connection information and other schema details. Once it's started, it allows you to begin bringing in real-time data. It is important to note that a feed is also a type of stream layer. This means that you can add a feed to a web map directly and begin to immediately visualize your data. This is what was done in the web map in order to visualize pedestrian observations. So, feeds enable real-time data ingestion, as well as provide for visualization capabilities and situational awareness. Suzanne?
Thanks very much, Greg. So the feed that he was authoring produced those pedestrian observations that we were looking at in the web map in the beginning. Just to recap a little bit, configuring a feed is the first step within ArcGIS Velocity when you're leveraging IoT data, which is simply accessing sensor data and bringing it in. Today, there's thousands of different sensors on the market, and being able to connect to that data and use it for organizations tends to involve either vendor-specific data applications that are siloed, or you have to build custom solutions to read in data and integrate it with enterprise systems. Configuring feeds in ArcGIS Velocity, as Greg showed, is an easy-to-use and guided workflow. So you can directly connect to external sources of observation data like the Cisco Kinetic Broker, also Internet of Things platforms like Azure and AWS, and third-party APIs as well. Feeds automatically derive the schema of the data by sampling the real-time stream, and then you can revise your data model on the fly. And when the feed is running and actively ingesting data, you can add them to a web map to see the real-time information on the fly and mash it up with other information. So a feed is both systems integration and situational awareness configured in minutes without writing any code. And bringing in data with feeds is just the first step. So next, with real-time analysis, you can do more than visualize your sensor data. You can immediately put it to use. In Velocity, a feed is an input to a real-time analytic, and these are used to transform, enrich, and detect incidents in data. Real-time analytics are a flexible model building capability that lets you combine tools and take different kinds of action. And there's three basic kinds of actions that you might take. You might store sensor observations over time to a feature layer. You can choose how long you want to store data for and whether you want to keep every observation or just the most recent for each track entity. You can also send notifications and alerts when particular incidents arise. And you can also send commands and triggers to external systems to trigger behavior. So with that, we'll go ahead and step back into this scenario with the Cisco Edge Intelligence System, where we're looking at different types of data coming in from the LiDAR system around intersections. And we're going to showcase some real-time analysis that you can do with this information. Greg?
Thank you, Suzanne. ArcGIS Velocity is an engine to analyze and take action on observational data. We achieve these capabilities using a new item type in ArcGIS Velocity called a real-time analytic. We'll continue with our theme of public safety from earlier to explore what a real-time analytic is and what it has to offer for analyzing and acting on observations. Now, many different types of organizations, such as cities or local governments, want to better understand when issues of public safety happen within their jurisdiction. Whether it's a 911 call, citizens reporting about road debris, or a flooding road, these entities want to know of this information as it happens so that they can take measures to respond accordingly, all in the interest of public safety. If we think back to the previous demonstration, we had configured a feed to begin ingesting and visualizing anonymous pedestrian movement around a key intersection in Las Vegas. With this same information available, we can begin to ask questions of our data using real-time analytic to gain situational awareness for public safety. One such question we might look to answer with this data is, when do pedestrians leave the crosswalk altogether and choose to remain within the intersection for an extended period of time? After all, anyone who remains in an intersection poses a safety risk for themselves and motorists alike. And as we can all imagine, this type of situation might be more commonplace in a city like Las Vegas, where pedestrian traffic is highly concentrated and individuals might be in a celebratory state of mind. You know the saying, what happens in Vegas stays in Vegas. So having said that, let's explore how we can use ArcGIS Velocity, and real-time analytics in particular, to explore our data and solve for this public safety question. So here we have our web map, which again is centered around the city of Las Vegas. We'll be returning to the intersection from the prior demonstration to closely see if any pedestrians enter and remain within that intersection for an extended period of time. Pedestrians that happen to meet this time and spatial criteria we've set will be uniquely identified and visualized as an incident. Now, just to be clear, we're not interested in situations where a pedestrian happens to sidestep the boundaries of a crosswalk just to get around a slower moving individual. Instead, we only want to be notified when a pedestrian is observed inside an intersection for a period of time greater than 5 seconds. So let's focus on this intersection now and enable the infrastructure layer to provide some more context. So here you can see the crosswalks are in green. These are the areas where pedestrians are permitted. In red, we have the intersection and streets where pedestrians are not permitted. For all intents and purposes, these are areas for vehicle traffic only. We are using the central intersection as a geofence for the purpose of our analysis. If a pedestrian is observed inside this central area for more than 5 seconds, again, our real-time analytic will create an incident that we can see and respond to. So let's now turn on our feed layer to begin visualizing the pedestrians again. And this time, we'll also enable our pedestrian incident layer to begin visualizing any unique incidents that may occur in this area. Now, as we monitor the situation on the ground, I will note that the data has been sped up for the purpose of this demo. You may also notice that because of the nature of the LiDAR sensor system, some pedestrians are observed only once in a crosswalk, whereas others are observed multiple times. To avoid any sort of false positive results that may come from just a single observation of an individual, a real-time analytic has been designed to only consider pedestrians with multiple observations in an intersection. We'll go into this a little bit more later. But as we continue to monitor the situation on the ground, we can see that one pedestrian has entered the intersection. As they remain in the intersection, our real-time analytic has now identified the condition and created an incident. By clicking on the incident point, we can see that the anonymous pedestrian observation has been enhanced with some incident information, such as a unique identifier string, an incident status that indicates it's ongoing, and an incident duration in seconds. And as the pedestrian moves away from the intersection, we could see the incident update in real time. As soon as this pedestrian leaves the area, the incident is closed altogether. It is important to point out that a real-time analytic can also be used to automatically notify others of this incident. For example, an email or text message could have been issued to a public safety officer to find out what's going on. The same type of message could also be sent to a CCTV operator to review what's happening in the intersection in real time, assuming that there's cameras. This is just one example of how we can explore this type of data in real time using a real-time analytic. I would now like to shift over to ArcGIS Velocity, where we'll explore how this real-time analytic was specifically configured. Here we have the homepage of ArcGIS Velocity again. If we wanted to, we could create a new real-time analytic from this page directly, or we could get started by creating one from an existing feed. But for now, I want to explore the existing real-time analytic that was used for the prior demonstration. So I'll access the real-time analytic page from the side menu here. You can see I already have a real-time analytic called Monitor Intersection Activity. Let's click on this and review the model. The simple model you see here is what allowed us to monitor pedestrian movement and create incidents when a pedestrian was found to be inside an intersection for a length of time. At the start of our model, we have the feed we created earlier called Cisco Pedestrian Observations. Again, we use this feed to pull in the anonymous pedestrian locations around the intersection. Below the feed, we have a feature layer data source called Las Vegas Infrastructure. This data source is simply bringing in the Las Vegas intersections as feature records. As I double-click on the node, you'll notice that I configured this data source to only pull in records from the feature layer whose type is of intersection. I chose to do this since we're not interested in using other types of infrastructure for our analysis, only intersections. For example, we don't want to be notified when a pedestrian intersects with a crosswalk, as that is expected behavior. But when this real-time analytic is running, both the pedestrian data and the intersection polygons are being passed to the first tool you see here called Detect Incidents. The Detect Incidents tool is used to evaluate incoming features against a set of opening and closing conditions, and it creates a unique incident for each continual set of observations that satisfy the condition. Let's open up the properties of this tool to understand what it's doing with this data. As we can see here, Detect Incidents is configured to create an incident anytime a pedestrian is observed intersecting with one of the Las Vegas intersections. Each pedestrian is assigned a unique global identifier by Cisco's system, and so we're able to use this as a track ID for this tool to monitor the ongoing status of a pedestrian's location. Once an incident has been identified and created, I then configured my real-time analytic to pass this information to another tool called Filter by Expression. This tool is used to filter features by an attribute expression using the arcade expression language. If I open this tool, you can see that I'm simply filtering for features where the incident duration is greater than 5 seconds. Now, if you all recall from earlier, we're not interested in responding to incidents from pedestrians who happen to momentarily sidestep into an intersection. They might do this because they want to get around a slower moving individual, or there's an obstruction in the crosswalk, such as an overextended vehicle. We have this filter by expression tool in place to remove a lot of the noise from the dataset by only passing features where the incident duration is greater than 5 seconds. Again, these are the only incidents we're concerned with knowing about, individuals who linger in the intersection. Once we filter the incidents of interest, our real-time analytic passes this to a stream layer called pedestrian incidents. This is what was used in the previous web map to uniquely symbolize incidents as they were happening. I could have visualized my incidents using a map or feature service, but I chose to use a stream layer for its near instantaneous visualization of incidents. While this was not shown in the demo directly, I also have a text message output configured as a part of this real-time analytic. I can use this to notify others of unique incidents using an externally accessible SMTP server to issue the text message. What makes this particularly powerful is that I can reference values from the incoming feature in the text message itself. For example, if my data has a field with the name of the intersection, I can construct my text message to notify individuals that an incident is happening on Clark and Main, as opposed to just notifying individuals of an incident at a generic intersection. So with all that being said, real-time analytics can be used to interpret streaming data from your feeds and perform exploratory analysis around the questions you have about your data. This sort of analysis happens in real time, which means that as observations of interest are found, such as incidents as we've seen here today, you can take action as it's happening. Suzanne?
Thanks so much, Greg. So real-time analytics provide processing horsepower to your tracking and sensor workflows. They're a solution that you can use instead of needing to build custom applications, which often have to incorporate streaming analytic code bases that are complex. Instead, any end user can assemble an end-to-end workflow like the one Greg was showing, which detects incidents and captures data in various ways. Real-time analytics work by processing each message from a feed continuously as it arrives, and they can leverage static data sources to serve as geofences or enrichment data. So the infrastructure for the intersections was the static geofences that Greg was using in that demonstration. With real-time analytics, you can combine different tools together into a workflow to ask different questions, and you can associate different output behavior with each question that you ask. In some cases, you might store data. In other cases, you might send alerts or a command to a third-party system. Real-time analytics as a capability are useful when your decision timeline is operational, when you need to know about something and take action immediately. Now, overall, there's extensive support in ArcGIS Velocity for different real-time and big data systems and various data formats. These are aimed at covering major commercial IoT platforms, as well as common real-time messaging technology. So for example, MQTT can be used as a bridge to bring in vehicle tracking data from vendors like Geotab. And an AWS or Azure IoT Hub can be leveraged to access data from a SCADA system and make it available for a system like Velocity. And polling a website allows you to access different sensor vendor APIs. Now, beyond real-time visualization and analysis, you can also work with data that you store over time. Feeds bring in and visualize real-time data, and these get used in real-time analytics for immediate awareness of incidents. Real-time analytics, of course, can store observations over time to a feature layer. Now, as data arrives in real time, historical data sets can grow to large volumes extremely quickly. And for that reason, ArcGIS Velocity is designed to grow with you. It includes fully configurable big data analytics so that you can process this information for trends. And these big data analytics can be traditional ad hoc analysis, but they can also be scheduled and run in near real time to support different kinds of workflows. So with that, we'll go ahead and show one more demonstration in this session. Greg's going to show us how you can put together a big data analytic to summarize information from Waze.
Thank you, Suzanne. In today's day and age, most, if not all of you out there, have some sort of smart device. Whether it's a smartphone or an embedded infotainment system in your car, we often rely on these devices to help with our necessary day-to-day transportation. We might use the information through these devices to simply navigate from point A to point B, or rather monitor road conditions for traffic jams, sudden detours, or for those of us with a lead foot, speed traps. And while this type of information is highly useful to us as individuals, the same could be said for different levels of government, especially as they look to better understand traffic patterns in their own jurisdictions. This information can be used to affect change over time through targeted infrastructure improvements. Now, it's often safe to assume that traffic is at its worst during peak rush hour times. That is certainly a given in most cases, but questions such as, where is traffic the worst, and to what measurable degree is traffic bad, are not as clear to us. However, using the power of ArcGIS Velocity and its big data analytic capabilities, we can begin to answer these questions through exploratory analysis of historical data. We'll be taking a look at this in action through the final demo of today's session. Here we have our web map that shows the greater area of Las Vegas, Nevada. In blue, we have lines that represent all the roads within this region. We're interested in examining these roads to identify where exactly that traffic jams are most frequent, and therefore in a way traffic is at its worst. So if we turn on our second layer here, we can begin to see all the reported traffic jams from the last 2 weeks. This data was obtained from Waze, which is a popular application for vehicle-based navigation and crowdsourced traffic information. And for those who are not familiar with Waze or how it works, as drivers navigate roads and report different traffic-related incidents to Waze, Waze in turn collects this information and shares it with other users of the application. Through a special partnership program called the Waze Connected Citizens Program, the same information that is shared among users can be made available to various government entities. This is done as part of a two-way data exchange where governments may be expected to provide Waze their own data about upcoming road closures, for example. But with that being said, we can see quite clearly that most of the traffic jam activity that has happened over the last 2 weeks has taken place on the major highways and roads. This is unlike the minor side streets where there's little to no traffic jam activity. And while it can be useful to just simply visualize where most of these incidents have happened, there's still the question of what road segments are the most heavily impacted. How do we make sense of the thousands of observations before us to pinpoint those areas in most need of attention? So let's enable our last layer to find this out. Here we have the output of our big data analytic from ArcGIS Velocity. The features in red represent the identified street segments where there have been one or more reported traffic jams over the last 2 weeks. The intensity or thickness of each line segment is based on a count of traffic jam incidents that happened on that street segment. Overall, we can see that the greatest concentration of reported traffic jams is along this stretch of highway roughly between downtown Las Vegas and the Strip. We could also see some significant activity to the southeast in Henderson, which is most likely because of the traffic to and from nearby Arizona. But what is particularly interesting about the outcome of this analysis is some significant outlier areas that we see throughout this region. These are places where traffic jams seem to be a regular occurrence and isn't happening on a major highway or thoroughfare. All of these are areas, though, that can be targeted for future infrastructure improvements to alleviate the problem. So let's work backwards now and take a look now at the big data analytic that was used to derive this information product. So here we are again at the ArcGIS Velocity homepage. If we navigate to the Big Data tab, we see that there's already a big data analytic that I had configured earlier called Waze Traffic Jam Trends. If I click on it, I have several different options available to me, but for now, I just want to review my model, so I'll click on Analysis. Now, the simple model you see here is what allowed us to derive traffic jam counts for each street segment and then visualize that information as feature records in the previous web map. At the start of our model, we have a feature layer data source called Las Vegas Waze Jam Observations. We use this data source to pull in all of the traffic jam observations from the last 2 weeks as feature records. If I double-click on the node, you'll notice that I configured this data source to only pull in records from the feature layer whose type is jam. I did this since we're not interested in using other types of alerts from Waze, such as weather events, in our analysis. Below this, we have another feature layer data source called Las Vegas Street Centerlines. This is simply bringing in all the street segments for the greater Las Vegas region from another feature layer. When I run this big data analytic, I'm choosing to have ArcGIS Velocity first pass the traffic jam points and the street polylines to a calculate distance tool. As the name implies, the calculate distance tool can be used to calculate the distance from a target feature, which in this case is our traffic jams, to the nearest feature in another data set, which is our street polylines. If I double click on this tool, we can see that I have configured it to calculate the distance between each traffic jam to the closest street center line that is within a range of 30 meters. This allows us to essentially snap our traffic jams to the closest street where the jam had occurred. Now, when a nearby street feature is identified and a distance value is calculated, I also configured this tool to join the object ID of the street to the original traffic jam record. This ensures that every processed traffic jam has the object ID of the street where the traffic jam had occurred. Since each traffic jam has been enhanced to include the object ID of its corresponding street, we can now move forward and join these records back to the street polyline using the original object ID to derive summary information, such as count. This is done using the Join Features tool. Join features can be used to combine two disjoint records if they share a common key value. In this scenario, I can join my original street data with the enhanced traffic jam data using the common object ID that they both now share from the streets layer. Since I'm performing a one-to-one join, any target street with multiple traffic jams that can join to it will produce only one feature with summary information. One of these summary fields is a total count of all traffic jam observations for that street segment. But in short, these joined records are passed to a map fields tool where we simply modify the name of our object ID field and then write this enhanced street record to the output feature layer called traffic jams per road segment. This was the layer we used to visualize road segments in red by the number of total reported traffic jams over the last 2 weeks. One final note that is important is that big data analytics can be scheduled to run in a recurring manner. This is useful if you want to run continuous analysis on growing historical datasets where new patterns or observations might come to surface. In our case here, we ran this big data analytic once using a dataset that contained traffic jam observations from just the last 2 weeks. If we wanted to, we could schedule this to run on a weekly basis as the data continues to accumulate. With this additional information, we can find more pinpointed areas where traffic jams are happening. But with that, I'll hand things back to Suzanne.
Thanks, Greg. So these big data analytics allow you to analyze information you store over time as it grows and becomes more and more unwieldy to work with. As Greg was pointing out, the traffic jam data wasn't especially high volume given the time period that it was collected over. But as these types of data sets are brought in over time, they get more onerous to run. And that's where these big data analytics can be helpful. They're running in the cloud and they parallelize information through Spark to get large jobs done quickly. With big data analytics, you can run analysis either on feature layers with data that you've stored in ArcGIS or on cloud big data stores that are fed from other organizational systems. Much like real-time analytics, you can stitch different tools together into an automated process and create many information products at the same time on the same data. And it's also important to note that the same outputs are available for big data analytics. So you can take automated action in your IoT system based on overall system status. Big data analytics are useful when your decision timelines are tactical, when you need to make a decision regularly based on standard practices. That's when you might involve scheduling. Or when your decision timelines are strategic, more traditionally when you need to learn over time and adjust larger approaches. There's a wide variety of spatiotemporal analysis tools included in ArcGIS Velocity. This includes tools for summarizing data, detecting different kinds of incidents and behavior, analyzing patterns, and leveraging spatial proximity. These are also largely the same tools available in GeoAnalytics Server today. But this also includes tools and concepts from GeoEvent Server that focus on tracking and movement analysis, like calculating motion statistics, summarizing journey and trip information, and snapping tracks to a road network. All of these tools can be used in big data analytics, and those that operate on a single message at a time can also work in real-time analysis. Now, both types of analytics in ArcGIS Velocity can generate output layers for visualization of time-enabled data. And there's 3 basic types. Stream layers visualize new information right as it arrives. So in this animated screenshot, we're looking at city buses moving around on their routes. Stream layers are based on WebSocket technology, so that means the map is actively connected to the server where the real-time data is flowing, and it's trigger-based, so new data is pushed to the map as it's received. Feature layers visualize data once it's been stored, and they're the most common type of layer used in ArcGIS. So to visualize data from feature layers in real time, you can set a refresh interval, and that requeries the information every few seconds. When you create a layer in ArcGIS Velocity, it also creates a special type of map image layer. This supports dynamic aggregation of high volume data so that you don't have to try to draw millions of features individually. These on-the-fly aggregations refine continuously as you pan and zoom. They show you increasing levels of detail in that way, and then they transition over to raw features when you have a low enough number of features in the map extent. So all of these layers can be created through analysis tasks and used in dashboards and applications to visualize information and improve situational awareness. So let's go ahead and wrap up our session today. So first, a few brief notes on licensing. We're taking a bundled licensing approach with ArcGIS Velocity. It's an annual subscription on top of ArcGIS Online. Velocity is an overall capability for an organization. Different users configure tasks to support simultaneous real-time and big data use cases. It's also tiered according to required data velocity and storage capacity as opposed to the number of users. So what does this mean for ArcGIS user types? Specifically, Velocity is managed by a web application, as you've seen in the demonstrations. This is the authoring environment for the new real-time and big data items. This web app is available to any creator or GIS professional in the organization, but you can control which users have access to it. Now, these analytics that are authored with ArcGIS Velocity and run in an automated way can generate different types of information products, like the stream layers, the feature layers, and the map image layers. These are available to all users in the organization to monitor data, to explore information, and to combine with other data sets in ArcGIS client apps. So Velocity essentially is a real-time and big data capability for the whole organization. It might be likely managed by a few people, but makes IoT insights and decision-making available to everyone. So to reiterate here, ArcGIS Velocity is a configurable real-time and big data engine for ArcGIS Online. It extends ArcGIS Online with the ability to easily bring in real-time data from different platforms and to put that data to immediate use. And the three primary capabilities are to ingest sensor data. There's wide support here for different messaging systems, data formats, and data velocity. To automate analytical processes and tradecraft on data. So whether you're bringing in data in real time, whether or not you need to produce information products in near real time with scheduling, or whether you need to analyze massive amounts of data over time. All of that is supported within ArcGIS Velocity. And then you can also drive specific action based on your analytical results, such as alerting. This is all configurable with familiar and powerful spatial analysis tools, and these capabilities can be applied to use cases that range from personnel tracking to asset monitoring to infrastructure protection. If you're looking for more information on ArcGIS Velocity, there's a lot of good content available and accessible. Check out our documentation for more details on supported feed types and analysis tools. There's a learn path available to get a feel for how to configure these real-time feeds and analytics. We're also publishing blogs regularly so you can understand different use cases in detail with using the product. And there's even more technical how-to content being added to our GeoNet site on a monthly basis, so be sure to check that out. As we wrap up here, please note that you can provide your feedback for this session by clicking on the session survey link directly below the video. We absolutely pay a lot of close attention to this feedback, and we're always looking to see how we can improve these sessions. So we look forward to hearing what you have to say. And with that, we'll go ahead and take any questions.
All right, thanks for joining us today in ArcGIS Velocity and Introduction session. We're going to start our Q&A for the next 15 minutes or so. I'm joined by Suzanne Foss and Gregory Christakos, the two presenters of this session. So let's kick it off with the first question. That was the most highly voted question here. What's the main difference between Velocity and GeoEvent server?
I can go ahead and take that one. So there are a lot of similarities between ArcGIS Velocity and GeoEvent, and a couple key differences. One major difference is really sort of the pattern for the ArcGIS ecosystem that they support today. So at a high level, GeoEvent server is for ArcGIS Enterprise, and ArcGIS Velocity is for ArcGIS Online. But that said, ArcGIS Velocity also has another major difference from GeoEvent Server in the sense that it is a combination of the incident detection and real-time analysis capabilities of GeoEvent and the big data analytics capabilities of GeoAnalytics Server. So essentially, Velocity also adds the ability to perform big data analytics on information that you've stored, but performing that in a SaaS environment, so that you don't necessarily have to roll your own big data architecture. And you can also schedule big data analytics to run on a regular basis.
Great. Okay, so kind of a follow-on from another attendee. Is this GeoEvent server but as a SaaS? What new capabilities does this have that you can't do with GeoEvent server?
So similar answer there. There conceptually, you can think of this as GeoEvent server, but as a SaaS. But the under the hood technology is entirely different. So the GeoEvent server capabilities have been rebuilt from the ground up with different architecture. And one of the reasons for this was to build it on architecture that could more fluidly scale to accommodate high velocity and high volume data. So Velocity fundamentally is another key differentiator between GeoEvent and ArcGIS Velocity, in addition to the big data analytics.
Great. So next question, does Velocity consume credits?
Good question. So we touched on this, not directly in this way towards the end of the presentation, but Velocity does not consume credits today because Velocity is licensed as a subscription that is more based on the total incoming rate of your data and the use cases that you need to support. So you have tiered subscription levels according to your data velocity, your data storage, and the number of things that you need to monitor.
Awesome. So how can I use Velocity to bring in data from vendor APIs that Velocity does not have an out-of-the-box connector or support for?
I can answer that one. That's a good question. So the primary method or way that you would bring in data from vendor APIs is using the feed type called the HTTP polar. Essentially, you can use it to tap into a URL or make a poll on a particular URL, and it supports custom parameters in order to sort of custom tailor what you're requesting of that vendor's API. Something that is coming up in the April release is OAuth 2 support. So that's just another way that the HTTP polar is being enhanced to connect to these APIs that you might be interested in.
Very good. All right, next question. How do I get started with Velocity?
I can take that one. So ArcGIS Velocity is licensed as an additional subscription on top of an ArcGIS Online subscription. So to get started with Velocity, you would have to have an ArcGIS Online subscription. And if you'd like to evaluate Velocity, you can get in touch with your account management to set up an evaluation. Once Velocity is turned on for your organization, either through licensing or an evaluation, there's some quick lessons that are part of the product documentation that step you through all the different concepts that Greg was going through in the demos, like how do you create a feed, what goes into building a real-time analytic, and so forth. So those are all available as free quick start capabilities. And in the long run, we'll probably be working to create training programs as well.
Great, thank you. Next one, is there a preferred IoT feed type for sensor data? What will be the easiest deployment for companies getting started with Velocity? From Mike.
That's a good question. I can take that one. And in many ways, this is one of those questions where the answer is the famous "it depends," which of course is not what anyone ever wants to hear. But sensor data comes in so many different forms that the way that we have built both GeoEvent and Velocity is to be able to integrate with the kinds of messaging systems that real-time data tends to flow over in the industry. One feed type to call out for sensor data would especially be the feed types that we have for other IoT platforms like Azure and AWS. So there are many sensor companies that are building integrations for Azure and AWS where the sensor data can be onboarded and brought into an organization's cloud SaaS environment through those brokers. And ArcGIS Velocity can read data from those directly. So essentially ArcGIS Velocity can be another downstream application within your IoT architecture.
Perfect. Next one, how are errors generally handled in Velocity when connectors are down, either on the input or the output side?
Oh, that's a good question too. Let me take this one. ArcGIS Velocity receives data in a lot of different ways. So there's fundamentally three ways of receiving real-time data. You can reach out to an external system and pull for data. You can be a receiver where data is pushed to you, or you can reach out to an external system and subscribe for data. So the ways in which errors are handled vary between these different methods. But one way it's handled, for example, if we're polling a system for data, is if we poll that system and we don't get a response as expected, we would have a series of retries. And if the system is down indefinitely, we would then skip that polling and write a log to the user. And in the long run, we are looking at enabling notification mechanisms for users that they can subscribe for if they want to understand when issues like that happen.
Great. Another good question here. Can you perform geofencing between two different real-time data streams?
I'll be happy to take that one. So the answer is currently no. However, we are introducing dynamic geofencing support to essentially achieve what's being asked here, and that's going to be coming with the June release.
Perfect. Next one, can Velocity be utilized in an offline system?
I can take that one. So today the answer is no. ArcGIS Velocity is a capability for ArcGIS Online only currently, but it is on the roadmap to enhance and offer ArcGIS Velocity for ArcGIS Enterprise. And in that paradigm, it would be able to be used in offline systems. If I'm reading that question correctly, and what is meant there is a system that is behind the firewall.
Okay. If you're visualizing AVL points in an ArcGIS Online web map, what outputs have the best performance for large amounts of data?
I could take that one. So with this kind of question, it really just depends, especially on kind of the volume or velocity of data that you're working with, as well as whether or not your data has unique tracks. So, you know, by default, if you're looking for kind of quick visualization of your features, you could use something like a stream service to kind of push that data from Velocity directly to the web map and kind of visualize that in a quick manner. But that has kind of a certain threshold depending on how many kind of unique tracks it is that you're trying to monitor or watch, or I should say visualize in the web map at any given point. And so once you kind of hit a certain threshold where you have large volumes of data, and that's going to depend, you would maybe then want to utilize something like a map service for its aggregation capabilities, right? So once you're getting data in the hundreds of thousands or millions of records, or maybe somewhere below that, that's where you'd want to utilize that in order to kind of visualize that data as discrete bins up to that certain threshold. So there's kind of a performance considerations for both. And then of course it depends on, what's the temporal nature of your data. So if you're trying to, visualize or show kind of a collection of data that's been collected over time, a map service would be, better suited there as well. So it really just depends. But if you'd like, we could talk a little bit more about your use case and kind of what you are thinking when it comes to large data, and we can discuss that a little bit more at the expo booth if you'd like.
This question, is there training available for Velocity?
There's not formal training available today within the ArcGIS educational services. We're looking to, in the long run, create a training program for Velocity. But there are free online tutorials that go through the product.
Great. Next one here. What's new in the latest release of ArcGIS Velocity?
Oh, a couple things. One of the things that's coming in our April release, Greg actually just mentioned, which is support for OAuth 2 when you're configuring a regular polling approach for asking for new data from a sensor vendor API. And then other new capabilities coming in the April release include a new real-time tool to detect gaps in data. So there was another question about, how does Velocity handle things when there's errors and inputs go up or down. Sometimes there is no way to tell if what you're receiving from is up or down, other than the fact that data isn't coming along. So the detect gaps tool can be used in a real-time analytic to understand when there's unexpected gaps in reporting of real-time information. Another new tool in ArcGIS Velocity in the latest release is generalized linear regression. So this is allowing in a big data analytic for you to bring in historical data, build a regression model to predict a dependent variable based on other attributes of the data. And then you can potentially use that model as new data comes in to generate predictions.
Great. Next question. Long term, is Velocity going to replace GeoEvent Server?
The answer to this is no. ArcGIS Velocity is a combination of GeoEvent and GeoAnalytics capabilities. But in ArcGIS Enterprise, GeoEvent and GeoAnalytics are separate products, and they will continue to remain to be that way. GeoEvent Server is a server-based software product, and we have a lot of customers who need single server software to perform their real-time processing. Velocity itself is a Kubernetes-based architecture. So when it comes to be integrated with ArcGIS Enterprise, it's going to be a product that runs on Kubernetes. And so there will continue to be GeoEvent as a server software to run real-time analysis.
Great. And second to last question here, how do you integrate with other IoT platforms?
I can take this one, and I'm thinking that the question is, how does ArcGIS Velocity integrate with IoT platforms, as opposed to how would the customer integrate Velocity with IoT platforms that are not necessarily supported. Fundamentally, there's IoT platforms that are supported out of the box. So two today are AWS IoT Core and Azure Event Hub, Azure IoT Hub. And in going forward on our roadmap, there's also plans to support other major IoT platforms out of the box. Another way that an end customer or partner could integrate with IoT platforms is by using lightweight functions in an IoT cloud-based system to push data directly to ArcGIS Velocity.
Cool.
That's one way.
And last question here, will there eventually be an on-premises version of Velocity?
The answer is yes. We are actively researching and beginning the work to create that as an alternative form of ArcGIS Velocity. And the timeline, the expected timeline for when that will be available for the market is still more or less being analyzed now.
Great. All right, that wraps up our Q&A, it looks like. All the questions have been answered. So thanks again for joining the introduction session on ArcGIS Velocity. And please click the link, session survey link at the bottom of the video here and take the survey. We value your feedback very much. And thanks again for joining us. Have a good rest of your conference.